session is Yogesh, who's going to tell us about supersymmetric deformations of ADS3 cross S3 and black hole hair.
Okay, thanks Anindya, and thanks to all the organizers, Justin, Anindya, and Chetan, for giving me this opportunity to talk. So the topic which I am going to talk about is not very recent, and I have also given some talks, and my student Shubhadeep might have also given the talk at NSM, part of it at least. Okay, so it may not be all new, okay, but hopefully it will be something of interest in later part of our talk. Okay, so first the usual preamble that about the black holes, that in string theory, okay, we have at least for the extremal black holes a very good way of explaining the entropy of the black holes. Okay. And the formula, it's a remarkable formula because it relates geometric quantity, which is the area, okay, to a counting problem. Okay. And this is the usual Bekenstein-Hawking result. Okay. And in string theory, after Strominger-Vafa, okay, we have a good explanation of matching both the sides. Okay. But because string theory is supposed to be theory of quantum gravity, okay, there are all these alpha prime and GS corrections. Okay. So both sides of this formula receive corrections. Okay. In particular, for higher derivative corrections, you have Walt's formula, okay, which Neil had talked about. Okay. And for defining the quantum corrections, okay, Ashok had one proposal of quantum entropy function, and these days this new gravitational index which Amitabh talked about, okay, that is being used to calculate the quantum corrections. Okay. So the best hope to have an exact relation of this form, okay, is for extremal black holes for obvious reasons. Okay. And it's a fortunate thing that, okay, this d micro, okay, actually it's an index. Okay. It's exactly known for many systems in string theory. Okay. So the question is that, okay, whether we can do the macroscopic calculation, okay, which matches with this d index, d micro, okay, or the index on the microscopic side. Okay. Now, okay. Now, Bekenstein-Hawking entropy, of course, is proportional to the area, okay, which is the horizon area, okay, and all these modifications, like Walt's modification, also includes only the horizon data, okay, and this quantum entropy function is also on the near horizon geometry only, okay. And for extremal black holes, we know that, okay, there is an infinite throat which separates the horizon from the asymptotically flat region. Okay, so we expect that, okay, we should be able to separate out the black hole entropy, okay, as something which is given only in terms of the horizon data. Okay. So an obvious conclusion is that, okay, two different black holes, okay, with the identical near horizon geometries should have identical macroscopic and microscopic degeneracies. Okay. Now Ashok, like many of the things in this area, okay, he first posed this problem that, okay, if we have a BMPV black hole, okay, and BMPV, if you recall, is given by a D1 D5 system with some momentum, okay, on some compact manifold, okay, with angular momentum also, and if you consider a rotating 4-dimensional BMPV, okay, in Kaluza-Klein monopole background, okay. So these two black holes, okay, they have I will show it also, but it's clear also from the fact that Taubner geometry, okay, that becomes like a flat space if you consider the inner region of that Taubner. Okay. So these two black holes, okay, they have the same near horizon geometry, okay, but if you do the counting, okay, as Ashok, Dilip, Justin, and many other people have shown that, okay, you have a different counting, okay, when you have the KK monopole also present, okay, compared to just the BMP black hole. Okay. So here is a counter example to the thing that I mentioned, that okay, identical near horizon geometries should lead to the same macroscopic and microscopic degeneracies. Okay. So the resolution which was proposed is to ascribe these extra degeneracies to this higher degrees of freedom, okay, and they are supposed to live outside the horizon. Okay. So for some reasons they were called the hare. And to compare two black holes, okay, we should first remove these outside degrees of freedom, these higher degrees of freedom, okay, and then calculate the horizon degrees, this d horizon, which is the count of the horizon degrees of freedom, okay, and that should be compared with the whatever we get from the horizon data, like quantum entropy function or Waltz formula. Okay. And for supersymmetric black holes, okay, these here, okay, can be identified as classical supersymmetric normalizable deformations of black hole solutions, okay, with support outside the horizon. Okay. So for simple cases, okay, we can just count the number of Hare modes, okay, even though, I mean, okay, nobody has done it, but I mean, it should be possible to do the geometric quantization over these solutions to get the d Hare in a more systematic way. Okay. Now just a little bit of history about this subject. So Navmita, Ipshita and Ashok, okay, they first proposed this problem, okay, and proposed the resolution also. Okay. So they showed that, okay, if you calculate this Z5D, the partition function for the horizon degrees of freedom, okay, okay, by dividing by this Hare partition function, okay, then that matches with the 4D, okay, partition function, okay, for the horizon degrees of freedom, which is obtained by this Z4D divided by Z4D Hare. Okay. And okay, they also did the perturbative construction of the Hare modes, okay, but later with Dilip and Ashok and myself, okay, we extended this by constructing these Hare modes as full supergravity solutions, okay, and we found that, okay, some of the perturbative modes, okay, which were constructed, okay, they became singular when you take the back reaction into account, okay, but fortunately, okay, it happened in such a way that this equality that I mentioned earlier, that is still true.
Isn't this somehow important to just get a separation of Z and Z Hare in some approximately free limit where you can really decouple these systems?
So that's where this fact that, okay, there's an infinite throat which separates the horizon from the outside, so that almost makes it the partition.
Then I'm confused about why you speak of nonlinear corrections, because in the free limit then there are, so I'm confused about how that's consistent with the second point you made, which is that some solution, some Hare becomes singular.
No, like, okay, they were perturbatively constructed, okay, but when you include the back reaction, okay, by trying to make them into full supergravity solutions, okay, one finds that, okay, these solutions are singular at horizon, okay, they have this null kind of singularity that, okay, they look regular, okay, but say Riemann tensor in a parallelly propagated frame, okay, that will be divergent.
What is worrying me is that if one includes back reaction, then even the factorization of the full partition function into a part which is near horizon and a part which is Hare, that itself you might worry about, does it work, right, if you start including all these corrections. So either one should somehow say that because one can go to some point in moduli space and compute something which is in the free limit, and then
no,
but then
this part is on the microscopic side, okay, so whatever index we calculate, okay, we count the number of Hare, okay, and this on the microscopic side we can do.
So there's a key.
And on the macroscopic side, okay, we have this infinite throat which separates the horizon from these outer degrees of freedom.
Then why does some, let me ask you this, if there's an infinite throat, why do some perturbative modes become singular? You can just take all perturbative modes and continue then? Why do some perturbative modes not have an extension to the full nonlinear element? What stops? What is the obstruction?
I mean, the obstruction is just that, okay, they disturb the horizon. Okay, so if you just consider the perturbative level, then you won't notice that. But if you include the back reaction, then they disturb the horizon. So then the definition of the hair is basically that something which keeps the horizon as it is, okay, and it's only outside.
You should go on. I just ask one final thing, which is that you just said that there's an infinite throat, which is why you can separate the outside and the inside, which is good. But then you also said that somehow some modes outside can disturb the horizon, but because there's an infinite throat, they shouldn't disturb the horizon.
So that's why, I mean, then that means that those modes are not exactly really just outside the horizon. Okay, their effect is sort of creeping in and disturbing the.
So those modes were thrown away, right?
Those modes. So those modes are not counted as here.
Yeah, what I'm confused about is either we should work in the free limit or we should work in the interactive theory. All this is conceptually very clear in the free limit. If one takes interactions into account and somehow interactions are important, then one might have thought interactions are important in many ways. It wouldn't be a box space structure and so on. So what's confusing me is we are saying interactions are important in a specific way for this effect but not for other effects. That's what is confusing me, but okay.
Okay, so let me just, we can discuss later. Okay, so we found that, okay, some hair were not really hair, okay, so one can throw them out, okay, and the rest of the hair, okay, which have smooth limit at the horizon, okay, so we include in this counting, okay, and the matching still happens, okay, and okay, later, okay, this was the simplest case, okay, for n equal to 4 CHL models, okay, with Suresh and Amitabh and Shanmugh Priya and Subranil, okay, we did this for the n equal to 4 CHL models, okay, and Justin and Aradhya also, okay, did it with the purpose of the positive, showing the positivity of the index, okay, and this hair removal, okay, becomes necessary, okay, without that, okay, many properties, okay, don't hold, okay. So now let me just discuss this classical solution, okay, because we constructed the supergravity solutions corresponding to the hair modes, okay. So this is the usual BMPV black hole, okay, for simplicity, okay, I've set angular momentum to 0, but everything can be taken into account later, okay. So these are the harmonic functions, okay, and we'll consider the Qn equal to Q5 limit, okay, so that, okay, we don't have to worry about the dilaton, okay, and in this limit, this 3-form field strength, okay, that becomes self-dual, okay, and in the near horizon limit, this metric, okay, takes this form, okay. Now, so this was for the BMPV with asymptotically flat spacetime, okay. But whenever we are talking about this 4D and 5D, okay, we'll always write the solutions as 6-dimensional solutions, okay, because a lot of things depend upon this this extra Y circle, okay. So for BMPV and Taubnet, of course, this is the Taubnet metric, okay, and the BMPV and Taubnet is given by this metric, okay, again the field strength is self-dual, okay, and one can easily show that, okay, in the small r limit, okay, this Taubnet is just the flat space type, okay, and we can take the again the near horizon limit of this thing, okay, and by some coordinate transformations we again get the same near horizon limit as for the case of BMPV in flat space time, okay. Now, okay, so since this near horizon region will be important to us, okay, so even though, okay, we can construct the hair modes for the full geometry, okay, let's do it in a slightly reverse way, that, okay, just first study the near horizon region and its deformations. So near horizon region, okay, is this metric, okay, which is, okay, we see this is just the ADS3 cross S3 metric. Okay. So this work is with Amitabh, who is here, and Shubhadeep, who is my student, okay, at NISER. Okay. So we just write down this ADS3 cross S3 in Poincare coordinates, okay, and just consider the deformations of various kind, okay, in this geometry. Okay. Both the 4D and 5D black holes, okay, they have this near horizon limit. Okay, so we'll consider various deformations. Okay. Even though one can do the fermionic deformations also, but in this talk, okay, I'll just focus on the bosonic ones. Okay. And we'll see that, okay, they will be basically the metric deformations, okay, and we can turn on the anti-self-dual field, okay, if you compactify on K3, okay, you get various anti-self-dual fields, okay, and we can turn them on, okay, and we'll see that, okay, these deformations, okay, they will match with the hair deformations. To construct these solutions with these deformations, okay, this Garfinkel-Vachaspati technique is quite useful. So this is a solution generating technique, okay, which says that, okay, if you are given a metric, okay, and some other fields, and if you have these null killing vector field with these properties, that, okay, it's null killing and hypersurface orthogonal, okay, then one can construct a new solution, okay, which is given by the old metric plus this extra term T, okay, and the killing one forms, okay, and this T just needs to satisfy the Laplace equation basically in the old metric, okay, and it shares the killing structure. Okay. So with this Garfinkel-Vachaspati technique, okay, and in our geometries, okay, we have such a null hypersurface orthogonal killing vector field, okay, so we can apply this transformation. Okay. So the effect of this is just to add this extra factor of h, okay, and so we take this is our killing vector field, okay, and this h is harmonic in the geometry, in the near horizon geometry that we have considered, okay, and we can expand in spherical harmonics, okay, get a equation just for the ADS part. Okay, and we can consider for various different L's, okay, and we'll see that, okay, they'll give rise to different modes. Okay, so these spherical harmonics, okay, we don't need any of these explicit form, but one doing the calculation, we need them. Okay.
So the aim here is to construct the BMPV with hair or something. What is the goal here?
So right now we are just considering ADS3 cross S3, which is the near horizon limit of both the 4D and 5D, and we are considering various deformations of it.
And but yeah, I'm asking why. What is the connection between this and the hair modes?
So because we'll see that, okay, hair modes, if you take the near horizon limit, okay, they will match on to what we'll construct now.
So these are basically the near horizon limits of hairy.
Yes, yeah. But in the ADS3 cross S3, things are much simpler. The full black hole geometry is more complicated, so it will be much easier here. Okay. So first is just the L case, L equal to 0 case, okay, where we have just the wave equation in ADS3. Okay, so that is just a trivial solution. Okay. And if you solve the equation that we get here, this equation for L equal to 0, okay, we get these solutions. Okay. And just by coordinate transformation, we can remove this B term, and this A term is basically there is a special kind of coordinate transformation which was first given by these people. Okay, so if we do that, then these transformations, okay, they are basically the gravity analog of the Brown-Henu kind of transformations. Okay. So they keep the asymptotic form of the metric same, okay, but change basically the h. Okay, and by these transformations, okay, we can remove, for example, this a of v times z square term. Okay. This s is the Schwarzian derivative of this coordinate transformation. which appears here. Okay. So for example, for constant case, okay, so we can start with the Poincare ADS metric. Okay.
Sorry.
Yeah.
So, yeah, is this a Brown-Hiller transformation or no?
Yes.
It is. I mean, it says that asymptotics are identity. Is it? Yeah, apart from
H.
I mean,
So leading order will be same. Okay, but this H. Yeah.
oh, the change in U is subleading.
Subleading, yeah.
Subleading is
Yeah.
Okay. Got it.
So just as a trivial example, okay, we consider it for constant A, and we can just find out the coordinate transformation by solving this equation. The Schwarzian derivative is equal to this. Okay, and that will give us the coordinate transformation, and that, for example, converts the Poincare ADS3 metric with this extra piece. Okay. Now let's consider the L equal to 1 case. Okay, again it's simple to solve. Okay, so we get two solutions. Okay, the Poincare horizon is at z going to infinity, and we see that, okay, if we put the spherical harmonics and this solution with the 1 by z, okay, that is the one, okay, which matches with the here in the full BMPV in flat space time one. Okay. On the other hand, even though this solution, okay, this preserves the ADS3 cross S3 asymptotics, okay, but this changes the horizon. Okay. So that's why we'll discard this solution. Okay, we'll keep this other one. Okay.
Sorry, yeah, can I go back to this slide? Yeah, so the if this is a Brown-Hiller transformation, then the information is entirely in F, right? The
Yes.
Brown-Hiller charge, the asymptotic charge is in
Yes.
in
Yeah.
F.
Yeah.
And
Yes. So under this coordinate transformation, for example, the stress tensor will change in the
like
usual way.
Schwarzian of-
Schwarzian. Yeah. Yeah.
Okay. All right. Please.
Okay, so we solve it for the L equal to 1 case, okay, and that basically that, okay, if instead of just the near horizon, okay, if we had done the Garfinkel-Vachaspati kind of transformation in the full geometry, okay, this is the term, okay, that will be the Hare mode there. Okay. So this L equal to 1 mode has a problem, okay, I'll just mention that in a few minutes. Okay. And on the other hand, if we consider this L equal to 2 mode, okay, so we get this as the solution. Okay, so this solution, okay, was obtained by Balasubramanian, Parsons and Ross, okay, when we were considering these asymptotically self-dual solutions, okay, but there they wanted to preserve the asymptotic conditions, okay, so they chose this part, okay, but for us, okay, the need to keep the horizon as it is, okay, that is the most important thing, okay, so we'll pick this 1 by z square part, okay, this is the one which will be regular at the horizon. If we consider the other one, okay, that has singularity at the horizon. Okay. So we'll see that, okay, this will modify the asymptotic conditions. Okay. Again, if we put the spherical harmonics and just you do some simple coordinate transformations, okay, again it matches with the Garfinkel-Vachaspati transformation of BMPV in Taubnet. Okay, so these two Hare modes, one is basically for the BMPV in Taubnet, okay, and one in BMPV in flat space. Okay, both of them, okay, we can obtain this way from ADS3 cross S3. Okay. Now the thing is that main difference is that, okay, this 1 by z square term doesn't preserve the ADS3 asymptotics, okay, and the resulting metric is not asymptotically ADS3 cross S3. Okay, if you include the Hare mode. Okay. Now one more deformation that we can do is that, okay, turn on this anti-self-dual field strength. Okay, and so they were discussed by Malsina and Strominger way back in '97. Okay, so they discussed the linearized limit. Okay, but we can use their equations. Okay, and because we have set there is no other scalar, okay, dilaton we have set to constant value, okay. So that's why, I mean, we just look at their equation, we see that only this mixed ADS sphere component of this three-form field strength, okay, that will be non-trivial, okay. The other ones, once you set the scalar to 0, okay, they also vanish, okay. And we solve this equation, okay, and this equation is basically, I mean, okay, in form language, okay, it's just the star 3 dB equal to eta b, okay, and this expansion in terms of vector spherical harmonics, okay, it's given like this, okay, and vector spherical harmonics, okay, this satisfy these conditions. So again, I mean, only non-trivial solution of this equation, okay, which keeps the horizon regular, will be this, okay. And just for future reference, okay, let me just mention that, okay, this equation, if you take one more derivative, this becomes like a massive vector field equation in ADS3, okay. And okay, so this solution, okay, we calculate the stress tensor corresponding to it, okay, and now include the back reaction by solving the Einstein equations with this T mu, okay, and we see that, okay, in the near horizon metric, okay, after including the back reaction, okay, this is the form of the metric that we get, okay. So this metric, okay, because of this.
The ADS3 language, when you say that regularity of the horizon, what does it mean just in terms of boundary conditions in ADS3? Does it mean that you put finiteness at the origin?
If finiteness at this Poincare horizon z equal to infinity. So this metric, okay, the simplest case of that is that you have this h of v, okay, which is just a constant, okay, and this metric, okay, it is not asymptotically ADS3 cross S3, okay. This metric is in fact what is known as this null warped ADS3 metric, okay, which has appeared in the other contexts like Kerr CFT, etc. Okay. And in fact, it's similar for this h equal to constant case, same as this three-dimensional Schrodinger metric also, where this exponent is z equal to 2. Okay. So in the dual field theory, basically it corresponds to turning on an irrelevant deformation. Okay. So basically that changes the IR properties in the bulk, that is asymptotics. Okay. We don't fully understand the field theory side of it, okay, but just from the gravity, that's what we can say. And again, this turning on this anti-subdual field, okay, we can check that, okay, if you do it in the full black hole geometry, okay, that can be done also, and that can be done because Taubnet space has this self-dual harmonic 2 form, okay, and with using that we can construct an anti-self-dual field deformation, okay, which is given just by some function of v times dv wedge omega Taubnet, okay. And when you can solve the full equations, okay, and again, because of this null killing vector nature of the geometry, okay, things simplify, okay, and we can solve this back reaction of this anti-self-dual field, okay, in Einstein equations, okay, to get this, okay. And if you take the near horizon limit, okay, it matches on to the what we have calculated just in ADS3 cross S3. But the main thing to note here is that this geometry is again not asymptotically ADS. Okay. Okay. So this is just the matching. Okay. Okay. So this I mentioned about that, okay, some modes becoming singular. Okay. So the point is that just the metric looks fine, okay, but that doesn't mean much, because I mean we require not just metric to be fine, but at least the Riemann tensor to be well defined, okay. And usually these null deformations, okay, they generate these parallelly propagated singularities, so we have to do a more careful analysis, okay. And in fact, the regularity can be discussed only in some good coordinates, okay. The coordinates in which this is written, okay, they are not good at the horizon, okay. So if we do this analysis for L equal to 1 Garfinkel-Vachaspati mode, okay, which was the one which matched to the BMPB in flat space time, okay, we find that, okay, metric can only be made C1, means once differentiable, okay, but not C2, okay, and in fact we can find several components of the Riemann tensor which diverge at the horizon. On the other hand, for L equal to 2 Garfinkel-Vachaspati and this two-form field deformation, okay, we can find good coordinates, okay, and even though some components of the second derivative of the metric become singular, but they never appear in the Riemann tensor. So physically, okay, these are acceptable Hare modes. Okay. So, okay, we have discussed many different type of equations for various Hare modes. Okay, so there's a sort of unified formalism. Okay, that is by these authors Bena, Giusto, Warner, and Shigemori. Okay, so they consider this minimal supergravity coupled to one tensor multiplet. Okay, and they showed that, okay, the metric can always be written in this particular form, okay, where this ds square 4 is what is known as base metric, okay, and usually we take it to be hyperkähler metric, okay, and these one forms beta, omega, and these scalars h and f. They are all given in terms of data on this 4D base space. So this formalism, okay, that is quite nice because it includes all the different kind of solutions that we have constructed. Okay. So that was the metric form. Okay. But in general, the three form, this this tensor multiplet field, three form field, okay, that can also be written in terms of this data on the base space. Okay. And all these various forms, okay, they are given in terms of this. So all these various solutions, okay, they can be embedded in this formalism. Okay, like for example, BMPB in flat space time. Okay, so that has the metric. Okay, we can embed this in this formalism. Okay, you get this form. Okay, if you consider BMPB in Taubnet, okay, then various harmonic functions Z1, Z2, okay, and this tensor multiplet field, okay, everything is given. And if you include the Garfinkel-Vachaspati modes, okay, or form field, okay, so all those can be embedded in here. So it's, and we'll see that if you consider more general solutions, then also this formalism, okay, all of them, as long as they have supersymmetry, have to fall into this class. Okay. So about the CFT side, okay, we don't have that much information, okay, but just by the looking at the follow-up behavior, okay, so we see that this tensor perturbation, the metric perturbation, okay, that basically corresponds to turning on a dimension 4 operator, okay, and this form field deformation, okay, that corresponds to turning on a dimension 3 operator. Okay, so both these are irrelevant operators. Okay, and in the bulk side, okay, they change the asymptotics. Okay, so the lesson we have learned here is that basically including the Hare modes means that, okay, changing the asymptotic boundary conditions from the ADS3 cross S3 to these new kind of asymptotic boundary conditions, this null warped ADS3 kind, okay, and on the field theory side, this means turning on these operators. So if we want to include the Hare modes, okay, we'll have to learn how to include these non-normalizable deformations. Okay. So there's still time, so let me just mention that, okay, how to do this Hare mode analysis. Okay, if instead of black hole, okay, we have these other objects which are the fuzzball geometries. Okay, so fuzzballs, I mean, are supposed to describe individual microstates. Okay, and they require that, okay, whenever gravity description is available, okay, the geometry is horizonless and non-singular. Okay. So this kind of Hare mode deformations, okay, they were considered by fuzzball people also. Okay, but the black hole thing that we have done, okay, that is quite different from the usual fuzzball hair kind of thing. Okay, and main difference is that, okay, because the fuzzballs don't have horizon, okay, they don't have any requirement of regularity. Okay, even though, I mean, they're supposed to be non-singular, so this condition we still have to impose. Okay. Another difference is that, okay, fuzzballs, okay, in the inner region, okay, they have this global ADS3 cross S3. Okay, on the other hand, for black holes, okay, we have this Poincaré ADS3 cross S3.
So your regularity was in the Poincaré horizon, right?
Yes, yeah.
So what?
Similar to the RST, maybe.
Yes. So here, I mean, okay, fuzzballs, so you require regularity everywhere. And the fuzzball hair that people had considered earlier, okay, they preserve the ADS3 boundary conditions. Okay, so unlike us, okay, they just choose the solution, okay, which preserves the, because they don't have any horizon to keep. Okay, so they choose the other solution, okay, and they preserve the ADS3 boundary conditions. So all solutions are asymptotically ADS3 cross S3, okay, which in our case basically corresponds to L equal to 0. Okay. So these fuzzball hair which people had earlier constructed, okay, they were like this. Okay. But from our experience with black holes, okay, we asked the question. Okay, so actually, Amitav, okay, he considered the question that, okay, whether fuzzballs can also have these hair kind of modes. Okay, so if we take the viewpoint that, okay, fuzzballs describe the horizon degrees of freedom, okay, then they should also have the hair modes. Okay, so he conjectured that, okay, the fuzzballs should also have these kind of hair modes, okay, because the corresponding black holes have. So here we saw that, okay, the difference between 4D and 5D black holes, that, okay, this 4D black hole had these two extra hair modes, one which corresponded to Garfinkel-Vachaspati hair, which was basically in the ADS limit L equal to 2 case. Okay. Just, that should be enough here. And anti-self dual field deformation, okay, which corresponded to this form field. And compared to that, okay, BMPB only had this L equal to 1 case, okay, which turned out to be singular. Okay, so we have this extra hair modes on the 4D side. Okay, so if the correspondence is correct, then, okay, this fuzzball geometry should also admit hair modes of these type. Okay.
The hair modes are important because the horizon, because they're kind of a correction to the horizon. But are we able to match the horizon entropy at all in these cases? These are cases with macroscopic horizons, right? The horizon
There are
entropy
no-
doesn't match with the counter fuzzballs in this case, if I understand. Horizon.
Yes, I mean, right till now, okay, people have not been able to construct enough states.
Isn't the question of hair then like a second order problem? And even at like the first order, the count is not matching. So if there is or there is not hair, might be like if there isn't hair, then it doesn't matter anyway. It's not matching, right? Or am I saying something wrong?
No, that is correct. That, okay, if but that is like, okay, so that is the sort of assumption that assuming that, okay, eventually somebody can do it. So that is like from the fuzzball point of view, that's the best case scenario. Okay, and I agree that it's possible that, okay, it doesn't work out. Then, okay, this construction will be allowed.
So, but in supergravity, I think in fact, one can show that you cannot construct.
In supergravity,
Deep recharge case, right?
Yes.
So I think, in that sense, the hair is like you're saying,
but I mean, okay, supposing if you include stringy corrections and if you include the internal directions and everything, supposing, I mean, best case scenario, if one is able to construct the microstates, then, okay, they should have corresponding hair modes. Okay, that's the.
Then maybe the hair might also depend on those same stringy corrections or whatever we construct.
Possibly, it's possible. But, okay.
So I did not understand what was sort of an invariant characterization of the difference between the hair that you are constructing versus maybe the fuzzball construction in general. Because it seems like your near horizon geometry is actually getting changed, right? I mean, there is
Yes.
irrelevant deformations and all that.
Yes.
So in that sense, I mean, what is the difference? Because it looks like you should look at the full full asymptotically flat solution. It looks like. So what is the difference between these hair modes and the standard first ball constructions that people have done? Because they are also somehow asymptotically flat.
Yeah, I mean these hair modes, okay, they have a black hole horizon inside.
Oh, I see.
But in the first ball, okay, there is nothing, no horizon inside.
I think Chethan is asking if you include the hair, you will get a new, the first ball solutions are not they're discussed in the full asymptotically flat case, right? So you have a first ball which is a full solution.
Yes.
So the hair seems to be just a new first ball which has the same asymptotic charges.
Yeah.
So there is no distinction. In the case of the black hole, you can say, okay, here's the black hole solution which has no hair, and then add some hair on top of it. But the first ball is more complicated. So it's like almost saying these are new first ball solutions that you're finding.
It will be like new first ball solution.
Is that this has a horizon always?
This doesn't have a horizon, but the first ball.
First ball doesn't have, but black
Not
hole.
the first ball, the one,
Black.
the previous one,
Huh.
the BMPV black hole.
No, so here it's really like that, okay, the horizon black hole, okay, outside there are some hair. Supposing we can say that, okay, the horizon can be replaced by this ensemble of fuzz balls, then, okay, with fuzz balls in the inside, there should also be hair outside.
Surely you'll have to correct the hair in the first ball independently.
I mean, of course, I mean, it won't be just the black hole here which will work here, it will be something different.
So the whole thing will be a new first ball solution.
It will be like,
Ball at the hair, it's a new first ball.
it's a new fuzz ball solution, but the usual fuzz balls, okay, if they correspond to the horizon degrees of freedom, okay, then whatever extra corrections, okay, they are outside.
Yeah, no, I understand. It might, maybe what you're saying is you have a new solution generating technique for fuzz balls. Which might not
Actually, we don't have it, but we'll give some hints. Okay, that's an ongoing work, so that's the aim, but we don't have the solution yet.
Can I just to sort of, do we always have to see these solutions as some microstates? That's not necessarily. So for example, I can take the viewpoint that, okay, I just find some configuration which can dual some CFT states.
Yes.
And this is a very precise way of generating a plus. So that's still true, right? No matter whether they come from the NKT or not.
They might or might not exist in the CFT. Maybe they can't be found, but that's a separate issue.
That's separate.
But maybe allow him to finish.
It's,
You go and finish, but sorry.
Ah,
just to make sure, no. Just because I'm sorry, I was sleeping, but the black holes did have a nice smooth horizon, right?
yes. In fact, we took some pain just to keep the horizon smooth.
Yeah.
Okay. So for this fuzz ball here, okay, so fuzz ball geometries are quite complicated. Okay, so we have not managed to do it the full hair construction in this case. Okay, but we have some hints. So let me just it's an incomplete work. Okay. So we consider the simplest fuzz ball analog of 4D black hole, which is this D1 D5 KK geometry, okay, which was obtained by Bena and Krauss. Okay, and it's of this particular form. Okay, and this is similar to what the earlier formalism that I had mentioned. Okay, it can be embedded there by just simple notational change. Okay, so the main thing about this is that, okay, if you go to the really deep inside the fuzz ball solution, okay, we get global ADS3 on the black hole side. Okay, we had this Poincare ADS, okay, and this global ADS3, okay, which corresponds to this NS sector vacuum in the CFT. Okay, so that is connected to the outside by a transformation, which is spectral flow in the field theory. Okay, on the gravity side, it just corresponds to a coordinate transformation. But basically, we have a global ADS3. You do spectral flow, and then you connect to get to this R sector, and this R sector is the one which connects to the outside asymptotically flat infinity. Okay. So as I mentioned, that the full Bena-Krauss geometry is quite challenging. Okay, I have not written down because they were taking like more than 2 pages just to write these A and S functions. Okay, so and of course they don't have a simple null killing vector which is hypersurface orthogonal, which was our solution generating technique. Okay, so we have not been able to construct the full solution, but in this global ADS3 cross S3 limit, okay, we have been able to make some progress. Okay, and the progress is minute, but the calculationally. It's just that we have been able to write this global ADS3 cross S3 in the form of this wave kind of solution that we discussed earlier. And again using these coordinate transformations of Brown-Henry kind. That because this global ADS3 cross S3 is like this negative m equal to -1 BTZ black hole. So using this coordinate transformation for that particular case, and solving this simple equation, we are able to get the global ADS3 cross S3 in this particular form. So this looks quite similar to the thing that we had except for the sign. But this is full global ADS3 cross S3, meaning that it's geodesically complete, full manifold, not the Poincare coordinates which are just a particular patch of this thing. So in this form of global ADS3 cross S3, we have a null killing vector, null hypersurface orthogonal killing vector, and we can do the Garfinkel-Vachisi transformation, and analyze various L modes, and that particular analysis is quite similar to what we did for the black hole, because the geometry became quite similar. So we have the same results for that L equal to 1 mode is singular, L equal to 2 mode is regular. We have not done the form field deformation yet, but that is also given this particular kind of geometry. That will be quite similar. So at least in this inner region, we have this deformation. But we have not done the full geometry yet, so that's why this is empty. So just to conclude, so this Hare modes were required to maintain this equality of this horizon degrees of freedom in the 4D and 5D black hole, and we saw by considering this near horizon limit that Hare modes can be thought as non-normalizable deformations which modify the asymptotic ADS3 cross S3 geometry. And it's important that these Hare modes, they are confined outside this near horizon region, and sort of growing towards the ADS boundary, but in the full black hole geometry they are still normalizable. And we extended the analysis from Poincare ADS to global ADS also, and at least in some limit the behavior of the fuzzball Hare modes. And these geometries like null warped ADS3 and this 3-dimensional Schrodinger matrix, they appear as the asymptotic geometries if you include the Hare modes. So since the asymptotic is changing, so it would be good to understand holographically, sort of with new asymptotics, what is the holographic dictionary in this case. And just a long-term goal that if this new gravitational path integral for index, whether that can be understood as the older this Ashok's quantum entropy function, if we include these Hare modes, can we reproduce the results which we obtained here. Thank you.